Okay, I'm just going to talk through these two examples. Again, we're dealing with scale factor here. Okay, so previously we've dealt with triangles inside triangles. What I'm going to look at today is triangles like this, where you've almost got the triangles kind of pointed in towards each other. It doesn't say it here in the examples, but again, we would look for that statement that the triangles are mathematically similar before we apply the maths we're about to apply. Right, okay, so looking at these diagrams, it can be quite complicated to see which sides are alike to get your reduction or enlargement scale factor. So what I'm going to do to begin with for these two equations is I'm actually just going to draw them out in a more conventional format. So what I want you to imagine doing is just grabbing these shapes, splitting them and rotating them down. Now if I did that, quick sketch there, I would get that. And now all I need to do is make sure I get the numbers on the correct sides in that diagram. So clearly we can see that the bases are 4 and 14. And if I was to rotate that in that way, the 5 would be here and the y would be there. And that maybe makes a diagram a wee bit easier to interpret. Okay, so hopefully you can see that I've got everything on the smaller triangle. I want y on the bigger triangle, so it's an enlargement scale factor for question 1. It's an enlargement scale factor, so it's big over small. Again, to get the enlargement scale factor, we want a like sides are the same. So in this example, we're going to deal with the base. So it's going to be 14 over 4. And we can simplify that down, dividing top and bottom by 2, we're going to get 7 over 2. Okay, and then it's just a case of taking the smaller equivalent side, in this example 5, and multiplying that by the scale factor. And again, we could do this without a calculator. 7 times 5 is 35, 35 divided by 2 is going to give us 17.5. We can deal with it as a multiplication of two fractions. Remember, you can write any whole number as a fraction by putting 1 on the denominator and then just doing the same calculation. So you get 35 upon 2, which is 17.5, and it's a length, so we're dealing with centimetres here. Okay, question 2, very similar. We're just finding a different side of the triangle, but just so you can see how this works again, I'll go through this one again. So again, I'm taking my two triangles, I'm splitting them and rotating them, and I'm drawing them out in a more conventional format. Smaller triangle and bigger triangle. Again, it should be quite obvious that the bases are x on the smaller triangle and 21 on the bigger triangle. And again, if I rotated them in that way when I was splitting them up, that bit there would be 16, and the other side there would be 24. Okay, again, I've got everything on the bigger triangle. I want x, the base of the smaller triangle, so it's a reduction scale factor. I like sides, well, my like sides this times are the kind of slanted sides. It's small over big because it's a reduction scale factor, so it's 16 over 24, and again we can simplify that, dividing top and bottom by 8. Okay, back to the usual now. We've got the reduction scale factor, we want x, so we take 21 and multiply it by the reduction scale factor, so 2/3 times 21. Again, if you want to write 21 out as a fraction, just 21 over 1, we can now just deal with fractional multiplication. Cross simplifying, dividing by 3, dividing by 3. 2 times 7 is 14, 14 over 1 times 1 is just 14. So we get 14 centimetres. Okay, and that's that.